Yeah. So what I'm saying is E2 is linearly independent with V1 and V2. They're linearly independent. Because I have three linearly independent vectors in R3, it's going to immediately become a basis. Why? Because every basis in R3 has to have three vectors. Now, I think the next thing we should try to see is if E1 would work. And let's say if E1 would work, how would we test that? It's the same idea here. So this will be -1, 2, 3, 1, -2, -2, and 1, 0, 0. And we can quickly put that in our calculator, just edit the matrix that you had originally. So this would be 1 instead. This would be 0. And also this works. This also works. The row reduced echelon form of this is I, which would indicate that V1, V2, and E1 are linearly independent. So we just showed you that I'm gonna call this B. I'm gonna call this B1. I'm gonna call this B2. I have another basis, V1, V2, E1. This works as well. Why does this work? Because I have three linearly independent vectors in a vector space that has three dimensions. That has a dimension of 3, or 3 degrees of freedom. So because I have three linearly independent vectors in a vector space that needs three vectors to be in the basis, then this constitutes immediately as the basis. So all I'm really testing for the whole time here was whether the vectors were linearly independent to V1 and V2. And we just showed that E1 and E2 are both linearly independent to these vectors. So the moment you're able to choose one of them to be linearly independent, boom, you can include that and extend this set of vectors to be linearly independent. So B2 is also linearly independent. And therefore, a basis for R3. Does that make sense? That makes sense, guys? Any questions about this? It may seem a little bit strange at first, this whole idea of linearly independent. You can extend it. You can extend a set of linearly independent vectors to a basis, and you can also reduce a spanning set to a basis. So remember, spanning sets can be reduced to create a basis for a vector space, and linearly independent sets can be extended to create a basis for a vector space. So you can extend linearly independent sets, and you can reduce spanning sets. Okay, so that's the connection. You can extend linearly independent sets, and you can reduce spanning sets to become bases of a vector space. And once we establish the dimension of a vector space, once we know that, then we only have to test one of the two conditions of being a basis. So in this case, we only cared about whether they were linearly independent, because once we were able to get three of those linearly independent vectors, then automatically it becomes a basis for that vector space. Okay. Any questions, guys? Tell me, tell me. Did I answer your question, Alexa, as to why is E2 not E3 and why E1 also works? Yes, you think, yeah, I know. It takes some time to think about it, to think about uh, why do we care about extending linearly independent vectors to become bases and not. But I just want to make sure you guys are clear that um, if you're in the span, if a vector is in the span of other vectors, you can never, in the moment you include that vector that's in the span to the other vectors, if you include it to that set, you can never be linearly independent. So again, linear independent vectors are vectors who are not in the span of the other vectors. It cannot be expressed as a linear combination of other vectors. Because if you are expressed as a linear combination of other vectors, you are no longer linearly independent. You become linearly dependent automatically. Okay. 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 So we've been talking about vector spaces. We've discussed several examples of vector spaces. We've touched upon a very important aspect of vector spaces, which are bases. A basis is a set of vectors that are linearly independent and that span the entire space. And so the number of vectors in a basis indicates the dimension of a vector space, and the dimension of a vector space is the same always, is always the same. Now we discussed the ways or how we can take linearly independent sets and extend them to create a new basis vector, a new basis set of vectors. And we can also take spanning sets and reduce them to create bases of a certain space. Okay. Now, beyond that, beyond just understanding what a basis is what's the point, right? What's the use? What's the utility of having different bases? Why can't we just stay with E1, E2, or the standard basis vectors for all of those different subspaces vector spaces that we discussed? Why not just stick with those and don't worry about any other basis ever again? Like, why do we have to care about other ones? Well, the thing is, sometimes rewriting vectors in terms of a basis, a particular kind of basis, is very much more insightful. Um, so now we're going to get into the computational aspect of bases. And so the idea here is called coordinates relative to a basis. This is quite important. This is quite important. Okay. Okay, so before we do that, we have to talk about something called the uniqueness of basis representation. We love talking about uniqueness, things that are uniquely represented. So again, if S is a set of vectors, V1, V2, all the way to Vn. So if S is a basis of a vector space V, then every vector V in V can be uniquely, key word here, It could be uniquely expressed as V equaling some linear combination. CNVN. This is pretty important, guys. Once you establish a basis for your vector space, right? So it's a basis is a set of vectors that are linearly independent and that span the whole space. That would mean that every vector in that vector space can be uniquely expressed as a linear combination of those basis vectors. The important thing here is it's unique. So if you have a basis, there's only one way to represent every other vector in that space uniquely using the vectors v1 through vn. There's only one way that you can select C1, C2, and Cn. There's only one way to do that. There's not more than one way. And that's very important that that's possible. Mir, yes.
This might be a stupid question. It is a stupid question, but how can vectors be linearly independent, but a solution exists to this?
Say that one more time. How can vectors be linearly independent, but what?
All the vectors must be linearly independent in order to be a basis.
Yes.
Yet all the constants are non-zero.
Okay, so you're right. Every basis have to have all of those vectors in that basis set have to be linearly independent. That's true. But then what are you saying?
But linear independence would imply that the only solution to this I knew it was a question.
So I think I know what you're trying to say. You're saying that the C1s here could be zero, right? Is that what you're saying? They could be non-zero.
No, what I was saying was that because I was confusing the linear independence definition. Basically, what I had replaced the v on the left side of the equation with a zero vector and saying, oh, the only solution is C1, C2, Cn must all be zero.
Yeah, which is true.
Right. Yeah, which is true. But for some reason, I have substituted that zero vector with the v vector and saying, oh, C1, C2, Cn must be zero. But I was wrong.
Yes. So actually, it reaffirms the point, right? That if you're a basis, right? And for example, if you were to express zero as the linear combinations of v1 through vn, there's only one unique way. These all have to be zeros. But what it's saying is that this is true not just for the zero vector. This is true for every other vector. There's only one way to select the CNs, the CIs, the coefficients. There's only one way. And that ties into what we already know, right? If we were to create a vector matrix equation, right, we would have all the V's, right, as columns. We would have C1 all the way to Cn, right, equals the column vector here. And then to find what these solutions are, we would multiply by the inverse of this coefficient matrix. And there's only going to be one solution for that. That's if the basis is indeed linearly independent and spanning. Okay, so the idea is this is uniquely expressed. Now the question is, how do we prove that? Proof. So the way sometimes we prove uniqueness is suppose that there were two different ones. So suppose V could be expressed as the following, as A1 V1 all the way to AN VN, right? And V had another representation, B1, V1, all the way to Bn, Vn. Does everybody see what the nature of this proof will be like? Suppose that there were two different arbitrary, there were two different representations for V, utilizing the same basis vectors. Does everybody see that? Now, if that were the case, right? If this were the case, then subtract the two equations. If we were to subtract this equation with this equation, what would happen? V minus V would be what? The zero vector? A1V1 minus B1V1 would be what? A1 minus B1 times V plus A2 minus B2 times V all the way to AN minus BN times VN. Sorry, this should be this. Does everybody see what's happening? So I am taking two linear combinations of V, supposing that there were two, and subtracting them. And now look what I got. I got this equation here. But what do I know about V1, V2, and Vn? There are bases, right? And since there are bases, what else do I know? They are, what's a characteristic of being a basis? The vectors are linearly independent. So we know that since we know that what? V1 all the way to Vn are linearly independent. If they're linearly independent, the only way that this here would equal zero, that this sum here would equal zero, is if what? Is if all of the what? All of the coefficients would have to equal zero. Isn't that true? Then it's not that A comma B is equal to zero. It's that AI minus BI equals zero for I goes from 1 through N. Does everybody see that? Because these are linearly independent vectors, each of these coefficients must equal zero because this equals zero. This is the linear independence way to show something's linearly independent, right? We find coefficients of vectors when you add them up as a linear combination to equal zero. The only possibility is if all the coefficients are zeros. That's the definition for being linearly independent. We already know that they're linearly independent. We're not showing that they're linearly independent. We're using the fact that they are already linearly independent because they're a basis. So because they're already linearly independent, this forces us to say that the coefficients must all equal zero because they're linearly independent. But if they're all equal to zero, then what's the immediate consequence after that? It must mean that what? AI must equal BI for all I 1 through N. If AI equals BI, what do we say? Were there really two different coefficients? It means that there is only one way to express a vector V as a linear combination of V1 through Vn. That's the result. Do you guys see the argument? So AI equals BI, this would mean that there is only one way, which is unique, to express V as a linear combination of V1 all the way through Vn. Does that make sense? And we end the proof. I think it's pretty nice. So for a fact, every basis, no matter which basis you choose, there's only one way to express every other vector in the vector space utilizing this linear combination of those vectors. There's only one way to do that. And this is a proof. Okay. So once we have that understood, then now we can make a definition. Now we can define, we can make a definition. If S is a set of vectors, V1 all the way to Vn, is, okay, and now this is kind of important, an ordered basis for a vector space. So order does matter, okay? In our world, order of the way that we select the vectors in our basis, it matters. Which one comes first, which one comes second, which one comes third. It's going to matter from here on out. For a vector space V, and V is in V, meaning that V can be written as a linear combination of C1, V1, all the way to C2, V2, and Cn, Vn. So establishing the fact that S is an ordered, so we're going to talk about ordered, is an ordered basis for a vector space V. And we have a vector in V can be written as a linear combination of V1 through Vn, because that's what the basis does. And it's uniquely defined by C1, C2, Cn. Then the scalars C1, C2, all the way to Cn are called, and this is the important thing, are called the coordinates of V relative to S. This is what we're defining. So the coordinates of V relative to the basis S are the coefficients or the scalars in front of V1, V2, Vn, all the way to Vn, that comes from the linear combination of those vectors to express our vector V. So this is denoted by the following, which is denoted by V, and then you put this in parentheses, relative to S is going to be the column vector C1, C2, all the way to Cn. Okay? Okay, guys? So the coordinates of V relative to S are the scalars, C1 all the way to Cn. So we start with something very, very straightforward. Example, when we talk about the basis, E1, E2, E3, right? And I have a vector V. call it 5. Yeah, 5. All right, as a comma, the limited form. 5, negative 1, 9. What's going to be the vector with respect to B? What's going to be that vector with respect to my standard basis? And this is what we've been using till now, or is it different? Well, we haven't talked about representing a vector relative to a basis as of yet. So we are going to be representing vectors in space relative to different bases. Right now, I'm giving you an example of a basis that we've been using since the beginning of the semester, which is a standard way, right? This is a standard basis. And now what would be the coordinates of our vector v? Yeah, up until now, we've only been using the standard basis every time. But now we'll be using different.
But that was the same. It's the same thing. Just now we're going to extend it to using non-standard bases, right?
Correct.
I'm sorry.
So for example, this.
I just wanted.
Oh no, that's fine. This is the standard basis, right? Standard basis for R3. Now, because it's standard basis, right? It's like the easy one. This is the nice basis. This is where things just fall into place. What is embedded in each of our vectors up until this point? Embedded every single time I write a vector, I'm using the basis E1, E2, E3. Why is that? What is V1 though? What is V? Isn't V simply 5E1 plus negative 1 E2 plus 9E3? Look what I just did here. I expressed the vector V as a linear combination of E1, E2, E3. And because E1, E2, E3 are so simple and nice, quote unquote, then the coefficients for each of these, or the scalars associated for each of these vectors, are just gleaned off of what I've just wrote. It's just obvious in a way, isn't it? So the coordinates relative to our standard basis is exactly the way we normally describe vectors to be. So this would be just 5, negative 1, 9. There's not much to say here, basically, what I'm trying to say. There's not much to say. It's exactly what you expect. Because every single time we express a vector in R3, R4, Rn, we're utilizing the standard basis as a reference. The standard basis is our reference. Now, let's use a new basis, though. Let's call this, so this is B1, right? Call this new basis. So this is relative to B1. Call this new basis the basis that we had shown. Which one did we show? V1, V2, like in this case here, we would show that negative 1, 2, 3, 1. Okay. So what if we have this instead? V1, V2, and E2. Oh, you know what? Before we do this, let me call B2 E2, E3, E1. What would be V relative to this new matrix, this new basis? Do you guys see the difference now? I just rearranged the order of the bases elements in our standard basis. I just rearranged them. I said E2 is first, E3 is next, and E1 is last. So, of course, writing this would still not be hard, right? This would be what? This would be negative 1 E2. This would be 9 E3. And this would be 5 E1, correct? But because we're now utilizing this idea of order, we're ordering our basis. We're saying E2 is first. So then my new coordinate is relative to the first vector, which is -1. That's scalar to -1 now. This will be 9, this will be 5. Do you guys understand what's going on? So the order of the basis matters a lot. It matters a lot. So from the beginning, I didn't mention anything about the order of the vectors. I didn't mention about why E1, E2, E3 are so useful. I just said, hey, this is it. This is what's called the basis vector. And you're like, oh yeah, E1, E2, it makes sense. X-axis, Y-axis, Z-axis. It's kind of natural to do this, right? It's natural to express vectors in such a way. But then the moment we start changing the order of them, we're going to change the way we represent them. The number here, -1 comes first, then 9, then 5. So this coordinate is relative, is the vector v relative to this new basis, which is still dealing with the same vectors, but now just the order switched up. And now the last way I want to do this is B3. Call B3 the same V1, V2, E2 as discussed in, as shown in previous example. Now we're talking about something completely different now, right? V1 was what? It was, I forget, what was V1? V1 was -1, 2, 3. So I want to show now what is my new vector V. What is V expressed as C1 V1 plus C2 V2 plus C3 E2. What is V again? V is 5, -1, 9, right? What is C, V1? V1 was -1, 2, 3. What's C, V2? It was 1, 2, -2, -2. And then what's E2? 0, 1, 0. What does this become? This becomes a matrix equation, -1, 2, 3, 1, -2, -2, 0, 1, 0. Multiply that by C1, C2, C3, and this is 5, -1, 9. Do you guys see that? I want to solve for the system of equations, which is equivalent to finding the coordinates that are relative to the new basis. Do you see now how this whole idea of solving matrix equations now is more than just solving the solution to a system of equations? Now we're trying to find the coordinates of a vector relative to a new basis. Do you see how this now is transformed to a different kind of problem? So then how do you find C1, C2, C3? Well, you have to find the inverse of A, right? This is A. You have to find inverse of A, multiply it by B. And you can do that quickly with your calculator. Create a 3x3 matrix, which I already had it. So a transformation of a basis forms a new basis. We're gonna definitely get into that next class. Definitely. So you're starting to see something, right? Something to see with transformations and bases. That's very interesting. So let me just finish this real quick. So 5, -1, 9. So when I do the matrix A inverse with B, I get 19, 24, 9. Hopefully you guys can confirm that that's what you guys got as well. So 19, 24, 9 is the solution to this system, right? To this matrix equation. But now this has an added significance. These are the coordinates, C1, C2, C3. These are the scalars for these vectors, which now has constituted as the coordinates of my vector with respect to this new, relative to this new ordered basis, which would be 19, 24, 9. Okay,